Good morning. Welcome to the third lecture of CE206 Module 5, Part 3 of Module 5 on Fluid Mechanics 2. This is for the second year students of Kerala Technological University, second year civil engineering students. The third part of Module 5 is going to be about a numerical method known as the direct step method. Now, in practice, it is often required to determine the distance up to which the surface profile of the gradually varied flow extends. So in the previous lectures, we learned the basics of gradually varied flow. We studied about the dynamic equation of gradually varied flow. We learned about the different types of surface profiles that can take place in a gradually varied flow. In this one, we are going to compute the length of the water surface or the length of the surface profile for a gradually varied flow, because this is necessary in practice. So in order to do this, we must integrate the dynamic equation of the gradually varied flow with numerical methods. So basically what we're doing is what usually is done in computers for computation of differential equations. So whenever you have differential equations and if you feed it to your computer cannot process the differential equation. It converts it into a numerical form. For example, dy by dx would be converted into x2 minus x1 divided by y2 minus y1 for the computer to calculate the values. So likewise, every differential equation is actually converted into a numerical form by the computer in order to compute the answer. So here we are going to convert the differential equation form of gradually varied flow into a numerical equation form to solve for the length of the GVF profile. So how it is done, I'll explain. So the direct step method is a numerical method that is used to determine the length of the GVF water surface profile. So this figure would be known to you. This was one figure that we had used in the first lecture of Module 5 in order to explain the dynamic equation of gradually varied flow. Here I am using the same figure to explain the numerical equation of direct step method. So I'll start from this figure. From this figure, I have got z1 plus y1 plus v1 squared by 2g equal to z2 plus y2 plus v2 squared by 2g minus sf into dx. Now, I bring all the z1, z2, y1, y2 and v1, v2 terms to one side and keep only sf dx on one side. So z1 minus z2 plus y1 minus y2 plus v1 squared by 2g minus v2 squared by 2g is given by minus sf into dx. Now I'm going to rearrange this equation a little bit. z1 minus z2 remains as it is, but the other terms I'm going to rearrange it as y1 plus v1 squared by 2g minus y2 plus v2 squared by 2g. Now you know the expression y plus v squared by 2g is specific energy. y1 plus v1 squared by 2g will be E1 and y2 plus v2 squared by 2g is E2. So that's my intention in clubbing them together like this. So this equation that we have got, I will write it as z1 minus z2 plus E1 minus E2 is equal to minus sf into dx. Now, if you look here, z1 minus z2, I'm going to write it as minus s0 into dx. Now, how did this come? z1 and z2, if I say z1 minus z2 by dx would give me the slope of the channel bottom, and the slope of the channel bottom is nothing but s0. I'm writing it with a negative sign because of the same reason I wrote sf with a negative sign, because slope is decreasing with increase in the distance, and so z1 minus z2 would be minus s0 into dx, and I'm going to replace z1 minus z2 in this expression with minus s0 into dx. So I will get minus s0 into dx plus E1 minus E2 is equal to minus sf into dx. I'll take s0 into dx to the other side. So E1 minus E2 would become s0 into dx minus sf into dx, or I will get dx is equal to E1 minus E2 divided by s0 minus sf. Now this is the differential equation form of the dynamic equation that I'm going to convert to the numerical equation form. So the numerical equation form would be Instead of dx, I have written delta x. Instead of E1 minus E2, I have written it as delta E. And S0 will remain as it is, but SF, I have written it as SF bar. I'll explain this to you in a little while. So delta x is equal to delta E divided by S0 minus SF bar is the equation that I'm going to use in order to do problems in direct step method. This is the numerical equation corresponding to the differential equation of dynamic or the differential equation that was the dynamic equation of gradually varied flow. So what is SF bar? SF bar is given by SF1 plus SF2 divided by 2. Now how this equation is used, or what is SF1 plus SF2, what is E1 minus E2, all this will make sense when you understand or look at it with the help of a figure. So that's what we'll be doing next. I'm going to explain how this equation can be computed numerically using a figure. So this is the equation that we are going to use in direct step method. Delta x is equal to delta E divided by S0 minus SF bar, where SF bar is SF1 plus SF2 divided by 2. So here I have a channel bottom with an obstruction. In place of an obstruction, I have written it as a weir, because a weir is a form of an obstruction. This is how the water is going to pass over the weir. So in the previous lectures, I had explained that this portion would be the gradually varied flow part of the flow, and this part would be the rapidly varied part of the flow. So I'm only concentrating on the GVF here, because I want to measure the length of the GVF profile. That is the length of the distance taken by the water to rise through a certain level. This distance I'm going to calculate using direct step method, and that is my objective here. So I'll explain how it is done. So I drew a line like this. This shows the gradual variation in the depth of the water. When I drew a horizontal line from the top of the weir, I got a slight variation in the depth. So initially let the depth be y1, and when it passes the weir, let the depth be y capital N. Now do not confuse this with normal depth. This is not normal depth. I've just written it as y subscript capital N. It's not the same as normal depth. Normal depth would be written as y subscript small n. This is y subscript capital N. That is another depth at the end of the GVF profile. Now my objective is to get the distance, horizontal distance from y1 till yn. That would give me the length of the GVF profile. So that is what I'm trying to do. So in order to do that, my next step, okay, before that, this distance between y1 and yn, it's known as yn minus y1, and this is known as the afflux. Afflux is the amount by which the water will rise behind the obstruction. So how much is the water rising behind the obstruction? That is known as afflux. Now this term is important because sometimes in the numerical problems they will mention afflux, so you should know what afflux is. It is the difference between the final depth and the initial depth of a gradually varied flow. So now in order to find out the length between y1 and yn, I'm going to take an intermediate depth here, which let it be y2. So let the x coordinate of y1 be x1 and x coordinate of y2 be x2. The distance, horizontal distance between y1 and y2, let it be equal to delta x. Now how do I find this delta x? To find delta x, I'm going to use this expression. Delta x is equal to delta E divided by S0 minus SF bar. What is delta E? Delta E is E1 minus E2. E1 is the specific energy corresponding to depth y1 given by y1 plus v1 squared by 2g, and E2 is the specific energy corresponding to the flow depth y2, which is given by y2 plus v2 squared by 2g. Now after I find out E1 and E2, I can find out E1 minus E2, which will give me delta E. That is the numerator of this equation. But in order to find out delta x, I also need the denominator. So my next step would be to find out the denominator of this equation. So bed slope S0 will be provided. It's a constant value. It will be provided to us. Now to find out SF bar, which is the average energy line slope, I know that SF bar is given by SF1 plus SF2 by 2. Now how do I find out SF? Let me use Manning's equation here. Manning's equation, V is equal to 1 by n r raised to 2 by 3 sf raised to 1 by 2. I've given subscripts. So corresponding to the velocity at section 1, V1 is given by 1 by n r1 raised to 2 by 3 sf1 raised to 1 by 2. On rearranging, I'll get sf1 is equal to n squared V1 squared divided by r1 raised to 4 by 3. And similarly, SF2 would be the energy line slope corresponding to the depth y2, which would be n squared V2 squared divided by r2 raised to 4 by 3. Capital N is Manning's constant. It is going to be constant for the channel, so it has no subscript, whereas velocity and hydraulic mean depth has a subscript. So I found out SF1 and SF2 corresponding to y1 and y2, so that I can find out SF bar. So now S0 minus SF bar also is known to me. So my next step would be to find out delta x. I know the numerator E1 minus E2 has been computed. I know the denominator SF bar has been computed. S0 minus SF bar will give me my denominator. So using the information, I will be able to calculate this distance between y1 and y2, which is delta x. But that is not the distance that I actually require. I require the total distance from y1 to y capital N. So this total distance, how do I get? What I do next is, I will take another flow depth. I will take another flow depth y3. Let the x-coordinate of y3 be x3, and the distance between y2 and y3, let it be delta x dash. So the same procedure that I followed to find out delta x using y1 and y2, I will be using for y2 and y3 to find out delta x dash. The same procedure I will be using to find out delta x dash. After I find out delta x dash, I will take the next flow depth, which is y4, and let the x coordinate of y4 be x4, and let the distance between y3 and y4 be delta x double dash. And using the same procedure, in place of y1 and y2, I will be having y3 and y4, because delta x double dash is the horizontal distance between y3 and y4. I'm going to follow the same procedure and find out delta x double dash, so on and so forth until I reach the final depth y capital N. So by adding all these small delta x together, what will I get? I will get the total length x. So this is what you are going to do in direct step method. You're going to break up your distances into small intervals, so that you will be able to calculate delta x dash, delta x double dash, and finally get the total length. Now there might be a doubt in at least some of your minds that why do we have to break it up into so many pieces? Why can't we simply take y1 and y capital N and do the whole procedure? The thing is that, look at the curve, it's not a straight line. It's varying very slowly. So if I took y1 and yn, the approximation that I would be doing would be very large. It would be a very large approximation to take y1 and yn and compute the length in one go. Okay, that is why I am breaking it up into small pieces to get the answer for the problem. So that is why we are first finding out delta x between y1 and y2, then finding out delta x dash between y2 and y3, so on and so forth. So you will understand in detail while we are working out a numerical problem. Okay, so we'll start with the numerical problems. A rectangular channel 10 meter wide carries a discharge of 30 meter cube per second. It is laid at a slope of 0.0001. That is bed slope. If at a section in this channel the depth is 1.6 meter, how far from the section will the depth be 2 meter? Take Manning's n equal to 0.015. So you're going to use direct step method to calculate the length between the depths 1.6 meter and 2 meter. So let's first take the given data. Given that B is 10 meter, Q, which is discharge, is 30 meter cube per second. The initial depth is 1.6 meter. The final depth is 2 meter. S0 is 0.0001. And Manning's constant is 0.015. These are the given values. So this is the channel bottom and the obstruction. This is the water surface profile. And you are supposed to find out this horizontal distance. This would be 1.6 meter, which is your initial depth. This would be 2 meter, which is your final depth. The flux would be 0.4 meter. It's not mentioned in the problem. But if it had been mentioned that flux is 0.4 meter, then also it would have been fine. You're supposed to find out the length between these two. Now how do you find it out? You will break it up into small. You'll take 1.7 meter, then you will take 1.8 meter, then you will take 1.9 meter, like that, and you will calculate small delta x's, and finally add them up together to get the total delta x. So here, yeah, that's what you're going to find out, the total x. Now to find x, we will be following a tabular column approach. So this tabular column might look a bit complicated to you, but once you understand it, it would be very simple. This are the given data. I have written it once again. Width is 10 meter, q is 30 meter cube per second, S0 is 0.0001, and n is equal to 0.015. So the table is going to appear all of a sudden, so it will look very large and might look complicated, but please work out or draw the table and start working out along with me. You will be finding it easy. So this is the table that is going to be used to find out the length of the GVF profile. So let's just count how many columns there are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 columns. There are 12 columns in this table, and under each column I have written the formula for y. I have not written because y is the depth. So this is y ranging from 1.6 to 2 meter, and I have broken it down into small depths: 1.6 meter, 1.7 meter, 1.8 meter, 1.9 meter, and 2 meter. Okay. Now the next column stands for the area corresponding to y. So the area it's a rectangular channel, so area would be width into depth, b into y. Wetted perimeter would be b plus 2 times y. Hydraulic mean depth would be area by wetted perimeter. Velocity would be given by q divided by area. Q is known to us, area has been computed, so q by area. Now the next column is energy. Energy is given by y plus v squared by 2g, and delta E is the difference between the energies corresponding to two different depths. So in the first column there will not be any delta E, E1 minus E2, because the next, only when you get an E2 will you be able to find out the difference. So E1 minus E2, first we have to find out E1 and E2, and corresponding to E2 we will be able to write E1 minus E2. SF, like we saw in the previous slide, n squared v squared by r raised to 4 by 3. So corresponding velocity have found out, corresponding hydraulic mean depth has been found out, and Manning's constant is known. So n squared v squared by r raised to 4 by 3 is the equation that you're going to use to find out SF. SF bar is SF1 plus SF2 divided by 2, and so in this column it is blank because this is the first depth. You will be able to average it only after you get two different depths, and so SF bar starts from this column onwards. S0 minus SF bar, since SF bar starts from here, S0 minus SF bar also starts from this column. Delta X is given by delta E divided by S0 minus SF bar, which is delta E divided by S0 minus SF bar, and so I'll just start here. We start with the depth 1.6 meter. Corresponding area, since width is 10 meter, corresponding area is 16 meter squared. B plus 2yi, we got 13.2 meter. And hydraulic mean depth is 16 divided by 13.2, 1.21 meter. Discharge is Q divided by A, 30 divided by 16, we got 1.88 meter per second. Energy 1.7792 meter by substituting this formula. SF 0.00061 by substituting this formula. That's all that you will get for the first reading. Now the second reading onwards, we will get all the columns, the values in all the columns. So 1.7 meter, which is I've taken an increment of 0.1. You can take a lower value also. You can take 1.65, 1.7, 1.75, 1.8 like that. But the number of columns will increase. The calculations required will also increase. So that is why I've taken lesser number of steps here. So 1.7 corresponds to an area of 17. Perimeter corresponds to 13.4. Hydraulic mean depth is A by P, corresponds to 1.27. Velocity is 30 divided by area, 1.76. And energy is Y2 plus V2 squared by 2G, corresponding to 1.7. So I've got E2 and I've got E1 here. So delta E would be easy to find out, E1 minus E2. So you got minus 0.0795. Now SF, using this formula n squared V2 squared by R2 raised to 4 by 3, I would be able to get this value. And so since I've got SF1 and SF2, I will be able to find out SF bar over here. Now once I get SF bar, S0 minus SF bar is easy. S0 is 0.0001. So S0 minus SF bar, I got it as minus 0.00046. Now delta E, which is this column, divided by S0 minus SF bar will give me the delta X between Y1 and Y2. So between 1.6 meter and 1.7 meter, the distance is 172.49005 meter. Now the next depth that I've considered is 1.8 meter. The next increment is 1.8. So 1.8 corresponds to 18 meter area, perimeter of 13.6 meter, 18 meter squared area, 13.6 meters the wetted perimeter. Hydraulic mean depth is 1.32 meter. Velocity Q by A is 1.67 meter. Energy would become, using Y3 plus V3 squared by 2G, I will get 1.9416 meter, and E1 minus E2 corresponding to this particular cell will be 1.8587 minus 1.9416. So the immediate energy before it minus the energy in this cell would give you delta E over here. Now once you get delta E, you can calculate SF, and using SF bar would be 0.00051 plus 0.00043 divided by 2. That is, these two values divided by 2 will give you this average value. So the immediately preceding cell plus this cell divided by 2. If I am going for SF bar in the next row, it is 0.00037 plus 0.00043 divided by 2. So on and so forth, I can calculate the values of SF bar. S0 minus SF bar also I will be able to calculate correspondingly, and I will be able to find out delta X corresponding to. So the delta X values mean that between 1.6 and 1.7 meter the distance is 172 meters. Between 1.7 and 1.8 meters the distance is 223 meters. Between 1.8 and 1.9 meters the distance is 286 meters. Between 1.9 and 2 meters the distance is 364 meters. So if I want a total length, I have to add the whole thing up. So instead of adding the whole thing up finally, what I have done is I have introduced a column capital X, which is the sum of delta X's. So it starts from the second row onwards. 172.49005, which was the delta X over here, would be the same value over here. Then it cumulates downwards. So 223 plus 172 would give you 396.33060. 286 plus 223 plus 172 will give you 683.04945. And 364 plus 286 plus 223 plus 172 would give you 1047.4271. So the cumulative, each value of delta X you are adding then and there, so that the final value, that is 1047.4271, would be the total sum of all the delta X's taken together. So the length of the gradually varied flow profile would be 1047.4271 meter. So you can just go through the table again, maybe pause the video and try to calculate. And once you get the hold of it, this table is a simple table. The value in the computations might be a bit lengthy. So try to keep the steps involved. You can see the number of steps involved to 5 or 6, not more than that. Because if you have 10 steps, the greater number of calculations you will have to do. Maybe 5 or 6 would be at the optimum value. If you go lesser than 5, your answer will not be accurate enough. So keep the number of steps between 5 and 6. That would be the best option. Now, so hence the length of the water profile is 1047.4271 meter or 1.047 kilometers. So for the water to rise from 1.6 meter to 2 meter, it takes 1 kilometer distance. That is what is being told by the or what is being obtained from the numerical problem. So let's take the next problem. In the above problem, determine the type of water surface profile. So this problem is actually a problem that was supposed to be asked alongside the previous lecture, because we studied about water surface profiles in the previous lecture. But usually it is seen that water surface profile types are always asked along with direct step method. So that is why I have involved this numerical or included this numerical in this particular lecture. So we got the length of the gradually varied flow profile. They have also asked us for the previous problem what would be the type of water surface profile, whether it would be an M1 curve or an M2 curve or an M3 curve, would it be S1, S2, S3, so on and so forth. We have to find out. So to find that out, first we should know the relative positions of critical depth level and normal depth level. So we should know YC and YN. So we know Q is equal to 30 meter cube per second. Manning's constant is 0.015. B is 10 meter. So small q, which is discharge per unit width, capital Q by B, is 3 meters squared per second. And directly we can use it to find out the critical depth. Critical depth is small q squared by G raised to 1 by 3. So 3 squared divided by 9.81 raised to 1 by 3, I will get critical depth to be 0.971 meter. If I wanted to determine normal depth Yn, I will use the Manning's equation, which is Q is equal to A by N R raised to 2 by 3 S naught raised to 1 by 2. So it's normal depth Yn, so the slope involved would be S naught. And so I'm going to write area, wetted perimeter, etc. in terms of normal depth. Here you can notice the how I have denoted normal depth Y subscript small n. Y subscript capital N that we had used for direct step method has nothing to do with normal depth. Normal depth is Y subscript small n. So area is equal to 10 into Y subscript small n. Wetted perimeter would be 10 plus 2 times Y subscript small n. So the hydraulic mean depth would be A by P. I would get this value. So applying Manning's equation, Q is equal to A by N into R raised to 2 by 3 into square root of S naught. Now you know how to solve this. You have done this in module 3. You have to use trial and error. So you have to draw a whole table and keep on putting values of Yn, compare LHS and RHS to find out the value of Yn. That is how you're going to get the value of Yn. I've not shown how Yn has been computed or how I've done the trial and error. I have not shown it in this PPT because of lack of space. So instead, I'm going to write solving by trial and error. I got the value as this. For your university exam, you will have to check by solving trial and error. You have to draw the whole table, compare LHS and RHS, and finally get the value of 2.97 meter using this trial and error method, because that will carry a lot of marks. The trial and error method to find out normal depth will carry a lot of marks. So you have to do that for due to time constraint as well as space constraint. I'm simply writing it like this. When you're doing it at home or when you're watching this lecture, you can pause this video and solve for normal depth on your own, get 2.97 meter and then only proceed. So now I'm comparing. I've got that normal depth is at 2.97 meter and critical depth is 0.972 meter. So normal depth level is below critical, normal depth level is above critical depth level. This corresponds to mild slope. So since Yn is greater than Yc, it is an M curve. Now in which zone does our curve fall? In zone 1, in zone 2 or zone 3? So if you remember, we had checked for the profile from 1.6 meter to 2 meter. 1.6 meter to 2 meter falls in zone 2 of the mild slope. So since we have analyzed the depths between 1.6 to 2 meter, it falls in zone 2. Hence the curve of water flow would be M2. It would be an M2 profile. So this is how you find out in what is the water surface profile. Okay. You find out Yc using Q squared by G raised to 1 by 3. You find out Yn using trial and error, and then you compare them, check whether they are steep sloped or mild sloped or critical sloped or whatever it is, and then check the zone in which your depth is falling and correspondingly name your curve. So we'll go on to another problem. This one is of a trapezoidal channel. So the formula for area and wetted perimeter would change. Remaining would be the same. Everything would be the same except for the formulas for area and wetted perimeter. So a trapezoidal channel having bottom width of 6 meter and side slope 2 horizontal is to 1 vertical. And Manning's n equal to 0.025 and bottom slope, that is bed slope, of 0.0016 carries a discharge of 10 meter cube per second. Compute the backwater profile created by a dam which backs up the water by 2 meters immediately behind the dam. So this is the question. So it is given, we'll write down the given data. B is 6 meter slope, N is 2 horizontal is to 1 vertical, so small letter n is equal to 2. You remember tan theta is equal to 1 by n. When we were studying a most economical trapezoidal channel, I had explained this to you. So small n is equal to 2. Capital Q is 10 meter cube per second. The final depth, Y capital N. Check the subscript, it's not normal depth. Y capital N is the last depth of the GVF profile, is given by 2 meter. S naught is 0.0016 and Manning's constant is 0.025. So if I am drawing the figure, this is the flow of water. Now I know that this depth just behind the dam is 2 meter. And I have to find out the distance of the length of the GVF profile. But the problem here is that I do not know the initial depth. If I want to do a direct step computation, I should know this depth as well as this depth, but I do not know the initial depth. So what do I do to find out the initial depth? I will consider the initial depth to be normal depth or uniform flow. That is, the gradually varied flow profile starts from uniform flow. After uniform flow, gradually varied flow starts. So at this point, at the starting point of GVF, I will assume that the flow depth is uniform. I have to find out normal depth using trial and error, and then only I will be able to apply direct step method to solve this problem. So first we'll solve for Yn. So assuming the flow starts from normal depth, we have to find out Yn. Now I use the formula, it's a trapezoidal channel, so Byn plus Nyn squared. So 6Yn plus 2Yn squared is area. Wetted perimeter is B plus 2Yn into root of 1 plus N squared. So I will get 6 plus 4.472 times Yn. Hydraulic mean depth is area by wetted perimeter. So I've directly substituted the values. According to Manning's equation, Q is equal to A by N R raised to 2 by 3 S naught raised to 1 by 2. Now I'm using S naught here because it is a normal depth that I'm going to find out. So it is uniform flow, and so here I can use the bed slope. So I'm substituting the values. Again, this has to be solved using trial and error. You are supposed to solve it using the lengthy process. I have not used the lengthy process. I'm directly just writing, solving by trial and error. But for the university exam, you have to solve this using trial and error, draw the table, check LHS and RHS, compare and find out Yn. So solving by trial and error, we will get Yn is equal to 0.963 meter. This is something that you're supposed to do. You will not get it in 2 steps. You have to work out one whole page for this. I'm taking the short way around. I'm using the shortcut. Not shortcut, I'm just skipping that part and I'm simply writing I got normal depth is equal to 0.963 meter. So now we can start with our direct step computation. These are the given data. B equal to 6 meter, N is equal to 2, Q equal to 10 meter cube per second, S naught is equal to 0.0016 and Manning's constant is 0.025. So this is the direct step table. The same 12 columns, Yi, area, wetted perimeter, hydraulic mean depth, velocity, energy, delta E, SF, SF bar, S naught minus SF bar, delta X and X. The same 12 columns I have kept here also. Formulas, there are slight changes because the trapezoidal channel, the area is By plus Ny squared. Wetted perimeter is B plus 2Y into root of 1 plus N squared. All the others remaining the same. Just these two are changing because it's a trapezoidal channel. Now look at the number of steps I've taken. I've started, my computation starts from 0.963 to 2 meter. 2 meter is given to me, so it has to end at 2 meter. And the initial depth is 0.963 meter. So I'm actually struggling to find a perfect uniform gap between them so that I can take 5 steps. Instead, what I'll do is I'll keep 0.963 as it is, and then the next step I'll take it as 1 meter, then 1.2 meter, then 1.4 meter, then 1.6, 1.8 and 2. Okay. So I have totally 1, 2, 3, 4, 5, 6, 7 steps. So corresponding to 0.963, I found out the values. There are some values missing because this is the first depth. And delta E I cannot find out, SF bar I cannot find out. And since I cannot find out SF bar, the remaining portion also I will not be able to find out for the first value of depth, but from the next value onwards all the columns can be filled. Now one very interesting fact here is that delta x has come out to be negative. Now this is fine because instead of going from 0.963 to 2, maybe the depth is going from 2 to 0.963. That is, it is the opposite way around. The flow depth is falling. So maybe that is why the negative sign is coming. That is okay. Does not matter. So even if you get a negative value, the magnitude of the value is correct. So even if you get a negative value, you can keep it there and continue with your work. You don't have to think about it. So corresponding to 1.2 meter, I have found out the values. Corresponding to 1.4 meter, I found out the values. Corresponding to 1.6, 1.8 and 2 meter, I found out the values. After finding out delta x, I can add up capital X by accumulating the values of delta x, and final value of capital X would be the sum of all these delta x values. I got it as 1205.4072. And so the length of the water profile is 1205.4072 meter or 1.2054 kilometer. So that's all with direct step method. These are a few questions for self-assessment that I've given based on direct step method. You can also refer previous year university question papers where questions on both rectangular channel as well as trapezoidal channel have been asked. They've also asked for water surface profile identification. Now, one very important thing about problems on direct step method is that they come for very high marks because they're such a lengthy process, usually come for 15 to 20 marks. So, practice it properly because everything follows the same process. You have to either find out normal depth or normal depth is given to you, but then the table and the values inside the readings inside the table are same. So, using this, you will be easily able to find out the answers. Not easily, I can't say you can easily find out the answers. It's a very lengthy, tiresome and boring procedure, but then finally it pays off. You will, once you get the final answer, you will get all the marks that you require to pass the exam, because 20 marks out of 100 is a huge thing. It decides whether you pass or fail. So I hope that you have understood the topic. If you have understood the topic, please attempt the questions for self-assessment. So thank you for listening, and I hope that you have understood.